My name is Chelsea. My name is Chelsea Craig. I am the past president of the Northeast SIA branch. Today is the final day of the AgUpdate event. We have two wonderful speakers for you today, Jeff Shino and Brianne McInnes. For articling agrologists that are attending, you can send your milestone sheets into info@sia.sk.ca at the completion of today's presentation and use this as a milestone event. 4 hours of CPD may be recorded for attending all 3 days. There will be a question period following each of today's presentations, so please type any questions you may have in the chat box and they will be answered at the end. I would like to give a huge shout out to all our sponsors. Without you, AgUpdate would not be possible. Thank you to our gold sponsors, Adama, Syngenta, Tigersol, Secan, the SIA, Sask Oats, New Farm, M&P and Melfort, Coke Agronomy Services, Flying Dutchman Aerial Services, Aerial Spraying, Corteva, UPL, Exceed Grain Marketing, Crop Pro Consulting, Bunge, BASF, and Affinity Credit Union. We would also like to thank our silver sponsors, Alpine, FP Genetics, FCC, Egg Scouter, and Borgo. Today, we are proud to present to you Dr. Jeff Schoenau. Jeff is a professor of soil fertility and professional agrologist who works in the Department of Soil Science at the University of Saskatchewan. He holds the Saskatchewan Ministry of Agriculture Soil Nutrient Management Chair in the College of Ag and Bioresources and is a fellow of the Agricultural Institute of Canada. He was born in Saskatchewan, raised on the family farm near Central Butte, and completed his undergraduate and graduate degrees in the College of Ag at the U of S. He continues to be involved in farming with his wife, Lynn. We look forward to hearing your presentation today, Jeff. Take it away.
Good day, everyone. My name's Jeff Schoenau. It's great to be here at the 2022 Northeast SIA branch AgUpdate, and I'll just switch over to my PowerPoint. My topic of discussion today, folks, is a look at soil fertility, fertilizers, and particularly emphasizing their management under drought conditions. I'm from the Department of Soil Science at the College of Agriculture and Bioresources at the University of Saskatchewan. Certainly, I think everyone's aware that the dry conditions were a major factor affecting crop production across much of Saskatchewan in 2021. In some of our field trials, we experienced firsthand the effect of that drought, as shown there. Blake Wyseth, a PhD student of mine, out in some field trials of his in south central Saskatchewan, and you can see the hard red spring wheat growth there. It almost looks like it's been harvested, but it hasn't been yet. It's only up to about the ankles, and certainly that those dry conditions and poor crop growth have a number of influences on what we see in the soil and what we can expect to see in the following year in 2022. And so that's what I'd like to focus on in my talk today. We think about dry soil conditions. They affect a number of important processes that go on in the soil. One of the first is that things just tend to slow down a lot as the soil becomes drier. The release rates of available nutrient from soil organic matter and out of crop residues are reduced. And that's because dry conditions in the soil reduce the activity of microorganisms and turnover of those nutrients. The other thing that happens when the soil is dry is that the nutrient solubility and the mobility, that is the ability of those nutrients to move in the soil, is also reduced. So that nutrient movement in the soil with water, as that water moves through the soil, and nutrients that are dissolved in that water like nitrate are dragged along, or through the water by diffusion, movement of nutrients like phosphorus through that water by diffusion, it's all reduced as that soil gets drier. Furthermore, from the plant end of things, the growth of the crop's roots, its subsequent ability then to take up nutrients from the soil profile, and overall removal as a result of that stress is reduced. And we were able to observe that firsthand this year in southern Saskatchewan in one of a graduate student projects looking at root growth. And under those drought conditions, root growth of hard red spring wheat that we saw was greatly restricted right at the beginning of the year by those very dry conditions. And that impairment of root growth at the beginning of the season also carried on throughout the season as well under those dry conditions. Those roots weren't able to grow very far, very fast in that soil profile as a result of those dry conditions. And that overall then influences the overall uptake and crop nutrient demand and removal under those very dry conditions. So the overall result of this is that we see reduced soil and fertilizer nutrient utilization and removal by the crop. On the positive side, those dry conditions do reduce the losses that we experience of nutrients like nitrogen by leaching and denitrification. The overall net effect of this, though, is what we see and certainly are seeing and have seen this past fall, a greater amount of residual available nutrient left behind at the end of the season. However, I do caution that generalizations can be dangerous, and indeed we do see quite a high degree of variability in residual available nutrient, both among fields and across individual fields as well. And we need to determine that carefully through soil testing. And I'm going to talk a little bit about that later on in my presentation. But certainly hearing reports, and we observe it in our field trials as well, and from folks who have done out there in the field and done sampling and soil testing, many fields from those drought-stricken areas are showing high supplies of available nutrient in samples that were taken last fall. And so that's something that we need to be thinking about as we move in the winter right now and into the spring of 2022. I think important to note that when moisture does return, and in some areas it has, and there were fall rains, even some rain later on in the season, and that when that moisture does return to dry soils, folks, we do see that things do spring back to life, so to speak. The microbial populations and activity in the soil go up when that precipitation is received. The microbes, the bugs come out of dormancy, and we get this burst of mineralization, this burst of conversion of nutrient from plant unavailable organic form into the plant available inorganic forms, something that is referred to as the Birch effect, named after the researcher who first reported this in scientific papers a number of years ago. And the other thing that when the moisture returns is that now those nutrients are better able to move in the soil, move outward from those fertilizer bands, and also out of surface residues, for example, potassium that's held in straw, laying there in the soil surface. Once we get some rains, that nutrient can move out of those surface residues down into the soil to where it's available for utilization by roots and also the microbial populations. And to look at this, I just draw from some of our past research work where we went out and monitored the supply of available nutrient over the season using PRS probes there, inserted into the soil in cylinders to exclude the roots, as shown there at the bottom of the slide. And going back to some of those measurements that we made, and since this is northeastern Saskatchewan, I managed to find some supply rates measured using PRS probes, in this case phosphate supply rates in the Melfort area over the season from the beginning of June to the middle of July. And this was conducted under different tillage systems, a minimum till, no-till, and conventional till of pea stubble. It was done in 1996. And actually the the spring was very dry at this particular site this year, and we can see there quite low supply rates in that period from June 1st to the middle of June. Getting drier then as we moved into the middle of June, end of June, and interestingly that no-till system there was showing up having higher supply rates of available phosphate, probably because reflecting a better moisture conservation there. And then in this study, right around the end of the June, there was a very good rain. And you can see the influence that entry of moisture into the soil through that rain had on substantially increasing the supply rates of available phosphate in that soil. For a couple of reasons. One, that moisture in the soil now gives that ability of that phosphate to move from other regions to that simulated root surface on that probe. And the other thing is that moisture probably also stimulated microbial activity, the production of enzymes, which encourage the release of phosphate into plant-available inorganic forms that the PRS probe root simulator could pick up. So showing that the very important role that soil moisture plays in turnover and availability of nutrients in the soil. That reduced crop yield and nutrient removal that we saw in 2021 from the drought translates into high residual nutrient in many fields, as I noted, and I think, combined with the high fertilizer prices that we're experiencing, really means that soil nutrient availability assessment is really more important probably than it's ever been this year. And last fall, I know there was a lot of soil samples taken out of the field and analyzed, assessed for the availability of nutrient, and that's very important to know where you're at. Under the drought conditions in particular, we always do need to, but especially under the conditions of the drought, we really need to be sampling our soils carefully to represent the field and accounting for that micro scale and macro scale variability. Microscale variability, I'm talking about the variability that in available nutrients in a soil, in a field, that can exist over a few centimeters, and in fact it can be huge, as well as the macro scale variability, the variability that occurs over meters or tens of meters or hundreds of meters across a field. And folks, sometimes that micro scale variability can be as big or even bigger than the macro scale variability. And overall, when it comes to soil fertility assessment through soil analysis, through soil testing, inadequate sampling, poor sampling is often the biggest source of error. And especially under drought conditions, we can have scenarios where we have a huge amount of microscale variability from old fertilizer bans, and a lot of microscale and a lot of macroscale variability, I should say, because of the patchiness of crop growth, some of that volunteer cereal and second growth canola that happened in the fall of 2021 that can create a lot of variability across that field area. And so that's something that we want to be thinking about, and certainly folks were thinking about when they did sampling in the fall, and thinking about as well going into the spring season. As I said, that microscale variability, that variation in available nutrient that can occur over just a few centimeters in soils can be very significant. And I refer back to an MSc project that was done by Blake Wyseth, and part of that project was looking at residual phosphorus distribution in soil after harvest, taking slabs or monoliths of soil as shown there, and sampling within the seed row, as well as moving out laterally, horizontally, and also vertically, and looking at the distribution of available nutrient as a function of within the seed row and moving out away from that seed row, and the fertilizer, in this case the phosphorus, was placed in that seed row. And what was the influence that we saw? Well, as shown here in these data here from sampling of those different points positioned within the seed row, and then 5 and 10 centimeters away horizontally, and then moving down 1 centimeter depth, 4 centimeters depth, 7 centimeter depth, 10 centimeter depth. We compared here the unfertilized control that didn't receive any phosphorus on the top, and we see there actually a relatively uniform distribution of phosphorus moving from the seed row out. In fact, there's evidence there of a little bit more depletion of available phosphorus in that unfertilized control within the seed row versus further away, probably because of a greater proliferation of roots right in that area. Where we had put down 20 pounds of P2O5 per acre as monoammonium phosphate in the seed row at spring. Looking at those levels in the seed row at fall, despite some very good soybean growth in this particular study and good yield and high uptake of phosphorus, we do see residual fertilizer phosphorus still left behind and elevated levels within that seed row compared to further away. And of course, as we would be looking at higher rates of applied nutrient in more concentrated bands outside of the seed row, we're liable to see even more of that large-scale variability or fluctuation in available nutrient, with a lot of residual nutrient left behind in those old fertilizer bands. So how do we account for micro and macro scale variability in a management unit that we're dealing with? Well, if we're thinking about microscale variability, variability across that seed bed over short distances, I think a good strategy is to sample across those seed rows. And that may involve taking a strip of soil and taking all of the soil out of there so that you have within your sample that you've taken, that composite sample, you have got both soil from the old fertilizer bands in the seed row as well as the soil in between. If you're taking cores of soil, you'll want to take lots of cores. I think an old rule of thumb I recall is if you're taking 10 cores, you want to have at least 2 of those cores coming out of the actual fertilizer band area itself, and the other 8 cores coming from the areas in between the bands in order to adequately have in a composite sample produced from that, a composite sample that you produced by combining those cores that truly reflects the average or the mean condition of fertility in that field area that you're sampling. On a macro scale, that is over several meters. If it's a management zone that you've identified, a polygon that you're out and you want to represent it well, you're going to need to take lots of samples from that zone. And in some of this work that we did a few years back, even an area, only 15 acres, we found that we may need to take as many as 40 to 80 cores to get that nutrient coefficient of variation below 10% level. And the coefficient of variation, the CV, is the standard deviation divided by the mean. And it takes a lot of cores to get that CV less than 10%. I think another interesting finding of this study as well, folks, is that in fields that had a history of variable rate application of nutrient, we didn't need to take as many cores as in the field where we had a constant rate applied. So it seemed like that variable rate application strategy was actually helping to reduce the variability in the field that we were evaluating in this work. I guess another question that comes up, can things change from this fall to next spring? Certainly they can. This is Saskatchewan. We can get a really big flip-flop from one set of conditions to another, and moving from very dry to very wet is indeed possible. And I remember not too many years ago, back in 2011, 2012, giving talks across Saskatchewan about how to manage soil fertility under flooded conditions, very wet conditions. So So yeah, things can change a lot from a dry season and going into the next spring. A lot of snowfall, a lot of early spring snow rains or snow melt and spring rains can indeed change the scenario significantly. And I guess some considerations related to that. First of all, we need to be aware that much of that residual available nitrogen that's left behind in the soil after harvest, that unused fertilizer, and by the fall of the year, even if it was applied as ammonium, urea in the spring of the year, it's going to have undergone nitrification, and it's going to be sitting there in the form of nitrate. And nitrate is susceptible to loss by leaching, denitrification, especially if it's wet. And I go back to some of the old trials that were conducted comparing fall-applied nitrate to spring applications. And that fall-applied nitrate, much higher losses and much lower recovery in the crop the following year or in the soil in the spring compared to ammonium, for example, that was applied especially late in the fall as anhydrous ammonia or even late fall banding of urea. So that nitrate that's hanging around there, that residual fertilizer end that by the fall has been converted into nitrate, we're going to be wanting to check and make sure, see if it's there, how much of it has carried over into spring at the time of seeding and crop demand. So I think it's a good idea to check a few fields in the spring, especially zones in the field like the low spots for efficiency of the carryover of that nutrient, of that nitrate that's there from that was there in the fall. Just what a proportion of that actually carried over into the spring. If it's not too wet, we may anticipate and see a good carryover, but again, be aware that since it's nitrate, there is the potential for that to be lost, especially if it's a wet spring. So we want to do some checking in a few fields. As far as phosphorus, potassium, folks, I think those should carry over effectively. What's sitting there in those residual fertilizer bands, there's really no leaching or gaseous losses for phosphorus and potassium, but recognize that it also won't be ideally positioned for root access by seedlings compared to the actual seed placement of it at the time of seeding. So we might see a little bit lower efficiency in recovery of P and K for that reason. For sulfur, sulfur present in the soil as sulfate could be leached, moved, redistributed into the profile. There is no potential for gaseous losses. I think we might expect under most circumstances some pretty good carryover efficiency of the sulfate. Elemental S that was applied in the 2021 season, those dry conditions probably restricted that oxidation, that conversion to sulfate somewhat. Elemental S is not subject to leaching, so it'll carry over into the next season, and we would anticipate that if the moisture conditions are good and temperature conditions are good, we would see a higher oxidation rate than what occurred under those dry conditions of 2021. That moves me on to fertilization and consideration of fertilization practices, and especially under dry conditions. We hope we're not going to be dealing with a drought scenario again this spring of 2022, but to think a little bit about that, and of course fertilizers are often the greatest input cost on a prairie farm, so we're always thinking about how can we get the most return from that fertilizer nutrient. And we think about fertilizers, actually a pretty broad range of materials that we can think of. We have our traditional commercial inorganic fertilizers, but we also have manures, we have some other byproducts or amendments, we have our biofertilizers, our microbial additives, and we can even think of a cropping system as a way of manipulating fertility. Fertilizers, especially if we're talking about a cropping system with a legume in it. So fertilizers, I guess I always like to think of as potentially anything that contains or adds available nutrient to the soil. And the 4 R's of fertilization, we always want to be keeping in mind that is the right form, the right application, the right timing, the right rate to get as much of that nutrient into the crop and have as little of it as possible lost from the system. So first, I guess to consider a little bit about commercial fertilizers, synthetic, chemical, inorganic fertilizers as they're sometimes termed. We have different forms of these fertilizers. We have all 3 phases there, solid, liquid, and gas. For nitrogen fertilizers, we have urea in the granular form, 4600. We have liquid formulation, the most common UAN solution, urea ammonium nitrate, 2800. And we also have nitrogen in the gaseous phase and hydrous ammonia gas, 8200. And all of these can work well. All of them will produce or contain nitrogen in the plant-available inorganic forms of ammonium and nitrate. So if we first think a little bit about application, folks, anhydrous ammonia, that gas, we want to get it into the ground and sealed to retain that ammonia. And in the case of granular urea, if we're putting it in the soil in a band, we want that covered up with soil to reduce the losses of ammonia that are produced when that urea breaks down. And we also need to be aware, we want to be mindful of damage potential if we have too high a rate too close to the seed. And dry conditions do tend to aggravate that damage potential. What happens to a granule of urea when we put it into the soil? It undergoes first a dissolution. It dissolves in a few hours or a couple of days into the soil water. And then what happens in that soil water is there's an enzyme called urease that's ubiquitous. It's everywhere, and that urease enzyme rapidly causes that urea to undergo hydrolysis and break down into ammonia gas. And when that ammonia gas formation occurs within the soil, that ammonia gas will then react with water in the soil and the particles to be converted into ammonium ion, which is retained and held in the soil. And ideally, that's what we want to have happen in order to get efficiency of retention of that nitrogen in the soil. And to that end, some of our enhanced efficiency strategies for nitrogen, like urease inhibitors, coated urea, can help in promoting that conversion of urea into ammonia gas and be retained in the soil as ammonium by slowing that process down. In the case of urease inhibitors, inhibiting that enzymatic hydrolysis for a period of time to allow water to move urea into the soil where that hydrolysis can take place and the ammonia then be retained by conversion into ammonium. The coated urea also helps slow that process down and gives a better opportunity then for that ammonia to undergo that conversion into the ammonium ion form where it is retained by being absorbed onto the particles of the soil. Now, when we're applying fertilizer nitrogen under dry soil conditions, folks, I think it's especially important to make sure that furrow is closing and sealing behind that opener. And that's especially true for anhydrous ammonia. A well-closed furrow reduces the risk of that ammonia loss to the atmosphere. Now, that's not just for anhydrous ammonia either, but also granular urea and the urea component of the end solutions. Coverage of that urea with soil gives an opportunity for that ammonia that's produced upon hydrolysis to react with soil water and the particles and be converted into the ammonium ion form and therefore be retained and available for plant utilization. Sometimes folks ask, well, in dry soils, is there enough water to actually have that process take place? And even in dry soils, generally there's enough water to get those urea granules to dissolve and to get that ammonia gas converted into ammonium ions. I have heard in 2021, I didn't verify it myself visually, but I did hear under some really, really dry conditions in southern Saskatchewan, folks were actually able to go into the soil quite a ways into the growing season. I even heard reports even in the fall could go in and actually find some urea granules in that soil that had still not undergone dissolution. It's got to be pretty dry in order to be able to find urea granules weeks or months after they've been applied. But generally, you've got enough water to undergo that dissolution. Liquid nitrogen forms may offer some small advantages under dry conditions, but as I say there, don't expect miracles. Nitrogen, in fact, is what we call a mobile nutrient in the soil. It moves long distances, meters, along with the water to wherever that water's going, and nitrogen will move with the water to the roots. Now, when it's dry, that water movement will slow down. That'll slow that movement with the overall nitrogen movement in the soil to where the roots are. But nitrogen's mobile. If you've got water moving to roots, the nitrogen will move along with it. Phosphorus and potassium are what we call the immobile nutrients, and we really want those placed where the roots can access early, giving that pop-up or starter effect is shown there, that early season increased vigor and growth of the crop when you've got some phosphorus in particular placed in the seed row or close by. You don't want to have those two nutrients hung up in dry topsoil. Ideally, you want to have them in the soil where the roots are, where the moisture is. That will maximize their availability. It enhances their ability to move to that root surface and be taken up. Just to show the importance of phosphorus placement here and getting that phosphorus into the soil to maximize the uptake and the yield response. As this was a study that was done in 2014, actually under pretty good moisture conditions in south central Saskatchewan, showing, and in this particular trial here it was for soybean, showing that having phosphorus in the soil, and that in soil was a combination, the mean of treatments of placed with the seed in the seed row, also a banded below the seed, a broadcast incorporate, averaged together, as shown here, termed collectively in soil placement, giving a significantly higher yield response of that crop, significantly higher P uptake and recovery compared to broadcast on the surface without any incorporation, just broadcast on the surface, which in fact the yield of was really not significantly different, nearly identical to what we saw with our control, where there was no phosphorus fertilizer added. So getting that phosphorus in the soil is important under really all moisture conditions in order to help allow that phosphorus to be close enough to where the roots are to be taken up and utilized in nutrition and give a yield response. Talking a little bit about fertilizer in the seed row to expand on that, overall it's a pretty good placement, but there is a limit. And we look at this in the context of what we call seed bed utilization, which is the opener spread divided by the row spacing. And this is the way that maximum safe rates of seed placed fertilizer are presented in our Saskatchewan Ministry of Agriculture guidelines. For example, using a disc type opener with a 1-inch spread on a 9-inch spacing, 1 divided by 9 gives 11% seed bed utilization. Our provincial guidelines say then maximum 10 pounds of nitrogen per acre in the seed row for canola. On the other hand, if we go with a opener which has a greater spread, like a sweep, a 3-inch spread, well then a 3-inch spread divided by the spacing in this example, 9-inch, 3 divided by 9 gives us a 33% seedbed utilization. Our provincial guidelines then allow for a maximum of 30 pounds of nitrogen per acre to be safely placed in the seed row for canola as urea. And so as we increase our seedbed utilization, our maximum safe rate that can be safely placed in the seed row goes up. Under those guidelines that are presented are for good moisture conditions. Folks, under dry conditions, we really want to be paying attention to these limits and recognizing that under dry conditions, we want to be especially cognizant and reducing our rates to account for the fact that dry conditions do tend to aggravate injury from seed row placed fertilizer. So the risk of crop injury from too much fertilizer placed too close to the seed indeed is increased under dry conditions. Why is that the case? Well, one is that nearly all fertilizers are salts, and the salt effect of that fertilizer on holding back moisture from that germinating seed or seedling is increased by dry conditions. And also for nitrogen fertilizers that produce a free ammonia gas, like urea, when it undergoes that hydrolysis in the soil, that ammonia gas, that free ammonia gas, is very toxic to seeds and seedlings. And if it's dry, less moisture, means a greater number of air-filled pores, means that there's more free ammonia gas in general, and it can also move further away and move outward and potentially cause injury, as shown in the diagram at the bottom of the slide. Again, we do have some potential ways to overcome this through some additives and enhanced efficiency approaches, such as inhibitors, coatings that would be added to urea fertilizer can reduce that seedling injury risk and reduce those nitrogen losses. So our urease inhibitors, again, which stop or reduce that rate of conversion of the urea into ammonia, slow it down, stop it for a period of time, can reduce that damage potential. Also polymer coatings, which slow that rate of that release of that urea salt out of that granule, can also be effective ways of reducing a seedling injury from seed row placed nitrogen fertilizer, and especially under those dry conditions where that effect is more pronounced. Overall, I think we do see that the greatest benefits from enhanced nitrogen efficiency products in reducing losses, often observed under high loss potential conditions. Surface applications, application in the fall, well in advance of the time of crop demand, excess moisture conditions. Those are the conditions where the enhanced efficiency products particularly shine. Now, if we think about dry conditions, under cold, dry conditions, with controlled release products, coated release products, for example, they will tend to release their available nutrient more slowly. And that's because the rate of dissolution, the microbial breakdown of the coating, tends to be slowed as that moisture content and the soil temperature decreases. And so under very dry conditions, that release rate might be slowed to the point that it actually may have somewhat of a detrimental effect on availability. Thinking about how conditions can vary so much over a field, we have these knolls, upslope areas that are dry and often high pH. Maybe part of the precision fertilization plan is to use some different enhanced efficiency products in different zones of a field, like the eroded knolls that are dry and high pH. A urease inhibitor there may be most appropriate to reduce volatilization losses, whereas when you get down in those depressional areas that are moist, maybe even wet, neutral pH, there a nitrification inhibitor or a coated product is liable, I think, to be most effective as an additive in reducing nitrogen losses. So we might think of precision fertilization, nitrogen fertilization, not only in terms of rate applied to different zones, differences in rate, but also even differences in products or additives. When it comes to timing, at the time of seeding, reduces that risk of loss before the crop can use it, and the single pass seeding and fertilizing system that is widely adopted here in Western Canada is certainly very efficient. If you are looking at pre-plant application, especially fall, anhydrous ammonia works well, also banded urea, and again, enhanced efficiency additives can help improve the efficiency of those fall applications. Moving the other way, application of fertilizer nitrogen after seeding, post-emergent. The nitrogen solutions are one example, especially a dribble band can work well. And under dry conditions at seeding, where things are looking kind of grim at that seeding time, and not really sure what might be encountered down the road in terms of the growing season, An appropriate risk management strategy might be a split application of nitrogen, so that you would put on your low moisture scenario nitrogen rate, a conservative rate before or at the time of seeding. And then if it does rain, the crop's coming on strong, make a post-emergent application of nitrogen to ensure that that crop is not limiting in the amount of nitrogen that it needs to achieve its yield potential, given a return to good conditions out there in the field. And I haven't said too much about forages, but I just want to share a little bit of some of our research results that we've obtained on forages. In this case, a post-emergent dribble band, or a dribble band onto a meadow brome stand. 2800 UAN solution applied here, 0, 50, and 100 pounds of N per acre. And as you can see there, we got a pretty good response of that meadow brome to a dribble band application in June. 50 pounds of N per acre, nearly doubling that meadow brome grass yield. And actually, as you can see there, very little difference whether it was coultered in or whether it was just dribbled on the surface in a surface dribble band. So surface dribble banding can actually be quite efficient, but note that in these studies, and we also had about 3 or 4 other sites, we always had a rain within a week after application that helped move that nitrogen from that surface band down into the soil. I think overall, we do need to be cognizant that in-soil placement of nitrogen does do some good things. It reduces the risk of gaseous losses. The tie-up by immobilization when the surface thatch is decomposing certainly improves the root access. Earlier post-emergent nitrogen applications we know will have more benefit on increasing the yield. Delayed application, a late post-emergent application, is going to have less yield impact. More benefit then shifts towards increasing the protein content. And we observed in our forage post-emergent dribble banding trials with UAN solution that we did see not at the higher end rates, not only a benefit in terms of yield response, but also a protein benefit as well. Moving on to rates. I think selecting rate is probably the most challenging aspect of fertility management. And how do we choose the appropriate rate? Well, things we need to be thinking about, of course, are the soil supply, which comes from our soil test in relation to plant demand. What's our yield potential there as a function of everything from variety to the water conditions, of course. Drier conditions, lower yield means lower plant demand. What kinds of losses might we anticipate to see? We need to be thinking about economics, of course, the price of the product relative to the price of the fertilizer, and the tolerance that a person has to risk. So lots of things to be thinking about there. I guess when it comes to moisture, which is our emphasis, it's always nice to know what that depth of moist soil is in the profile in the spring of the year. And now we also have the ability to effectively do real-time monitoring of soil moisture throughout the profile with sensors, and provide huge amounts of data on soil moisture not only in the spring but over the growing season. That capability exists out there and is being employed. I guess in its simplest sense, just knowing how much moist soil you've got can tell you about your stored soil moisture, and it's your stored soil moisture along with your growing season precipitation that really dictates how much water you're going to have available to that crop. Depth of moist soil and how much stored soil moisture can be predicted and adjusted based on the texture. A sandy soil, a foot of moist soil is equivalent to about 0.75 inches of available water per foot of moist soil. A loamy textured soil with more clay, 1.5 inches of available water per foot of moist soil. And a clay soil, and those clay soils do tend to store the greatest amount of available water. A foot of moist soil there equates to 2 inches of available water. And there are yield equations which are used to predict the yield based on the stored soil moisture plus the growing season precipitation. These are some old equations back from the 1990s. This is for open pollinated canola, dark brown soil zone, open pollinated canola. Obviously a little bit out of date, but when we plug some numbers into these, we can see, very poor conditions for moisture, not much stored soil moisture, 4 inches of growing season water, 8 bushels per acre, compared to very good, where you got 4 inches of stored soil moisture, now 12 inches of growing season precipitation, 42 bushels per acre. I think to update these types of equations, these types of multipliers like 3 need to be adjusted upwards to maybe 3.5, but it shows the basic concept that it's really stored soil moisture plus the growing season precipitation that together really is a very strong predictor of yield potential for crops here in Saskatchewan and Western Canada. And there's going to be different multipliers and different subtractor factors for different crops. And of course, those always need to be updated based on improvements in genetics and in our ability also to conserve moisture in the soil through our modern approaches to farming, like the direct seeding, the zero-till, which also increases or enhances the water use efficiency compared to the old days when the soil was tilled extensively. Economics is important, using a response curve to apply the rate of fertilizer nutrient that's going to maximize the net return. As shown here, response curves, response of canola to added fertilizer under good moisture, wet conditions versus dry conditions. You can see that response curve is steeper. It starts to level off at a higher fertilizer end rate under wet conditions versus dry, and then that optimum rate where the last dollar spent gives you a dollar worth of increased yield is at a higher rate under those more optimum moisture conditions where your yield potential is higher. We do need to be thinking about risk. Of course, those higher target yields that we would set does equate into a greater risk of achieving that. And the last thing I'd like to talk a little bit about in relation to thinking about fertilizer and making good use of nutrient in the soil, crop selection, and under this category, thinking particularly about some considerations when thinking about growing legumes on high residual N soils. Where we had cereal or an oilseed crop, and a good example of that are some trials we had in south central Saskatchewan. You can see there in the pictures there, this was about end of June. You can see some pretty poor crop growth there. Stunted wheat, only about 8 or 10 inches high, and then translating into the fall there on the right-hand side, didn't get much better. A lot of residual nitrogen left behind in that cereal stubble, and oilseed stubble as well. So if you're now looking at thinking about growing a pulse crop like pea on that, or lentil, in the northeastern Saskatchewan, it's probably going to be peas, or maybe soybean, or faba bean. What's the implications there? Growing that legume, that pulse crop, on that soil with a high amount of residual available nitrogen. Well, I think we need to think about how that is probably going to influence the proportion of nitrogen in that plant derived from biological nitrogen fixation. What we're talking about here, talking about biological nitrogen fixation, or BNF, is the nitrogen that's derived from the air and converted into usable plant nitrogen through the symbiosis that takes place with the rhizobium bacteria that lives in those nodules on legume roots that we can see when we pull up a legume plant, a pea plant, a soybean plant, a faba bean plant, and take a look at the roots, and we see those nodules on there. We cut them open, we see that red color as shown there. That red color indicates that we have lots of leg hemoglobin, which is a compound that helps shield the enzyme responsible for nitrogen fixation from oxygen and allows it to carry out that fixation. Beefy red nodules inside indicate active nodules actively fixing nitrogen in there for the legume plant. That biological nitrogen fixation can account for as much as 70 to 80% of the nitrogen in that legume plant. And so on average, under good conditions for nitrogen fixation, meaning low soil available N, good fertility of other nutrients, and good growing season conditions, 70 to 80% of that nitrogen in that legume comes from the atmosphere via that biological fixation process. A very important and economically significant contribution to the nitrogen and the yield in that legume plant, and also to the crops that follow. I know in some of our work we've even seen that contribution to even get as high as 90%. I think in some alfalfa where we did some assessments. But we need to have the right conditions in order to maximize that contribution of nitrogen for free, so to speak, from the air through the activity of that rhizobium bacterium in that nodule on those legume roots. What's the implications of growing a pulse crop like pea on a soil that has high available nitrogen levels? Well, the main impact, folks, is that the contribution from biological nitrogen fixation will be reduced. The crop will probably do okay. If the available nitrogen's really high, I've seen where you can get excessive vegetative growth and some lodging issues. But the main thing is that when you've got high available nitrogen in that soil, what happens is that the legume will just simply use the inorganic N from the soil as a nitrogen source, rather than sending photosynthate to the rhizobia to allow that nitrogen fixation to occur. Because energetically, it's cheaper for the plant to just take up the inorganic N from the soil and use it, rather than give up some of its energy to give to the rhizobia to fix it from the air. So it's easier for the plant to just use the inorganic N in the soil, and so if there's lots there, that's what it does. And the contribution from nitrogen fixation, folks, is reduced accordingly. And so if you've got a lot of residual inorganic N sitting there in the soil, in order to actually probably get the best benefit from it, you'd want to grow a cereal crop or an oil seed which can't fix its nitrogen from the air and has to rely on that nitrogen that comes from the soil or the fertilizer. But in the case of the legume, if the inorganic N isn't present there, then it sets out to derive that nitrogen from the atmosphere through that symbiosis with rhizobia, and that nitrogen from the air comes largely, I guess you might say, for free, although there is some energy expenditure, but it does come into that plant and into that system as an external source. It's fertilizer nitrogen that it's nitrogen to the plant, in effect a sort of fertilizer that you don't need to pay for. Some general rules of thumb in this area, folks, is if the soil available nitrogen, we're talking here about the top foot, and the fertilizer nitrogen is greater than about 30 pounds of nitrogen per acre, nitrogen fixation starts to be affected. You start to see some reductions occurring. And if you've got greater than about 50 pounds of available nitrogen per acre being supplied, available in that top foot, you're going to see a significant reduction in the proportion of nitrogen in that plant that is coming from fixation, and a greater utilization of the proportional utilization of the nitrogen in the soil. And that comes from the Ministry of Agriculture Inoculation of Pulse Crops fact sheet. And just to show you this in some data that was obtained by one of my MSc students, Archini Dona, 3 years ago, looking at the proportion of soybean nitrogen that was derived from biological fixation, what we term percent NDFA, in a field trial that we did in southern Saskatchewan. And this was a soil that had about 22 kilograms of nitrate nitrogen per hectare, about 20 pounds of nitrate nitrogen per acre in the top 12 inches before seeding and fertilization. And what we had here is we had 4 different rates of fertilizer, a 0 treatment, and then 10, 20, and 30 kilograms of N and kilograms of P2O5 per hectare added as a blend, a fertilizer blend of urea and monoammonium phosphate that was added at the time of seeding. And what you can see here, folks, is you can see there that as we added nitrogen, when we got up to 30 kilograms of N per hectare, or 30 pounds of nitrogen per acre added to that soybean, along with the 22 pounds of nitrate nitrogen per acre, 22 kilograms per hectare that we had at the start, so adding up to about 50 in that top foot. As you can see there, we went from 80% of the nitrogen in that soybean plant derived from fixation, a significant drop down to 71%. So that highest rate of added fertilizer, nitrogen, significantly decreased the proportion of nitrogen in that soybean plant that was derived for free, so to speak, from fixation. So it really reduces the legume benefit of the free N from atmosphere if you've got a lot of available N in the soil, and as a consequence, the plant simply uses that instead of carrying out the fixation. So if you want to get the maximum amount of nitrogen derived from fixation, you want to be growing your legumes on soil that are low in available nitrogen in order to maximize that external input from fixation of atmospheric N. Just to show this here in some pictures we took and we always set up a demonstration for the soil fertility and fertilizer students that they work with, showing the impact of high levels of available nitrogen on impeding nitrogen fixation in legumes. This is with soybean here. These are soybeans that were inoculated, growing on a soil with low available N and no nitrogen added. You can see there, folks, lots of nodules on those roots there. Reddish color indicating active fixation. And soybeans here, inoculated again, growing in a pot. In this case, a high rate of nitrogen fertilizer added as ammonium nitrate solution, equivalent to about 200 kilograms of N per hectare. Here, folks, we see absolutely no nodules, no evidence of nitrogen fixation occurring at all on the roots of that soybean. The last thing that I'd like to talk just a little bit about is weed control and nutrient availability. And I think this also has some implications as well in helping to understand the impact of weeds that would grow, for example, late in the fall, or even volunteer or second growth of crop. When it comes to weeds, those weeds are certainly nutrient robbers. They utilize and compete not only for water but also for nutrient. And to show this was a study that we did about 10 years ago, a little over 10 years now, I guess, looking at the uptake of nutrients by wild oats, a kind of a moderate infestation of wild oats. How much nitrogen and phosphorus did they take up over time? The age of the wild oats all the way from 1 week to 10 week, and you can see here, even in the early stages, some rapid uptake of both nitrogen and phosphorus incorporation into the wild oat plants. By the time they got to be about 2 months old, we had over 100 pounds of nitrogen per acre and over 20 pounds of P2O5 per acre in the biomass of those wild oats. So that's some significant competition, and it starts to happen pretty early on. The other thing that we looked at in this study was the recovery of nitrogen and phosphorus from the above ground wild oat residue by wheat. Really trying to simulate, you might say, if you terminate those wild oats in the crop at different ages of the wild oat, how much of that nutrient is going to be released and made available to that wheat crop in which those wild oats were growing in. And as you can see here, that percent recovery of nitrogen in that wild oat residue decreased significantly as time went on. And even only 1 week old wild oats didn't get a lot of recovery of the nitrogen by the wheat from that above ground wild oat dead biomass. And that's probably in part as well due to a fairly high carbon to nitrogen ratio of that wild oat material, even at a fairly young age. The recovery of the phosphorus by the wheat in that wild oat residue was better than what we saw for the nitrogen. But as you can see as well, as those wild oats got older, just like for the nitrogen, that recovery decreased as those wild oats got older. And I think the same thing if you were looking at volunteer cereal growth or a second growth of an oil seed like canola. When those plants get older, the carbon to nitrogen ratio tends to widen out. The carbon to phosphorus ratio widens out. Less soluble phosphorus in that residue. The rate of release from those old plants is going to be less than what you get from the young plants. From a weed control standpoint, early weed control significantly reduced weed nutrient uptake in competition with the crops for nutrient and water to begin with. And also that early weed control should promote more rapid recycling of the nutrient back into available forms for crop use. And again, just thinking of all these different strategies that we can use to try to maximize the amount of nutrient that we've got in available form in the soil for the crop to use when it needs it. So we really want to be using every opportunity out there, folks, to retain, recycle, and reclaim those nutrients on your farm. I think when we're talking about moisture conditions, whether it's wet, dry, or in between. So, of course, fertilizer nutrients, we really want to use them. We don't want to lose them. Get them in the crop. And it will rain again, I'm sure. There's some areas that are still pretty dry, particularly in southern Saskatchewan in the fall, and not a lot of snowfall yet, but it will rain again, and hopefully not too much like we saw earlier on in the early 2010, 2011, 2012 period. So with that, I'd like to thank the SIA organizers of this event for inviting me to give a presentation, and thank you all for your attention. Thank you.
Thank you so much, Jeff, for that wonderful presentation. If anyone has any questions, please type them in the chat box, and Mackenzie is going to read those off for us.
Okay, first question. Have you done any work with biostimulants such as Utrisha N or Envita? And what's your thoughts on them?
I haven't done any work myself with the biostimulants. Some of the biostimulants, their mode of action is a kind of a hormonal activity to increase root growth, which can potentially improve water uptake, can improve nutrient uptake. And I think, that can be a benefit. To what benefit really depends on the conditions. I think, stimulation of root growth under some circumstances can be really beneficial. In other cases, maybe not so much. So yeah, I think they have a role, particularly in encouraging growth of plants like in portions like the roots that can be a particular advantage under some conditions.
Awesome. Would there be any advantage to inoculate in high nitrogen soils?
I think that inoculation is always a good practice regardless, even though the high available N will tend to discourage the onset of nodule development and the nitrogen fixation process. There may be areas within that field that are actually low in available nitrogen, despite the fact that they, on average across that field, test high. And those areas, I think, could still benefit and would benefit from having that rhizobium present in the popular numbers. So I think inoculation is a good practice anytime you grow a legume. And even under high available land, there may be portions of that field that are low in available land where you may see that response from that inoculant.
Thank you. How much less fertilizer should we be placing with the seed to avoid injury under dry conditions? Is there a specific percentage of safe rates we should be using?
In any work that we've done, we've always done it on under controlled environment conditions, under good moisture, and so that's what the guidelines are developed based on, for example. And certainly as it gets drier, that yield, that injury potential is increased. To what extent you would drop that back, what percentage, I don't really have a good feel for that. But you know, I'm thinking that when you get into really dry conditions, you know, you'd probably be wanting to drop those back by, you know, 20-30% might be kind of a ballpark.
Okay, and one more question here. Some work this past year showed no response to N rate increases, not surprising with the drought, but did see a positive yield response to increased P and K rates. What are your thoughts on this? Less solubilized soil P, so more reliance on fertilizer P?
Yeah, and actually that's an interesting observation, and one that I think probably maybe does relate to the positional availability of that fertilizer P in relation to the soil P. If you've got that fertilizer in that concentrated band and under those dry conditions, maybe particularly helping to keep more of it in solution and close to where the roots of that germinating seed and seedling are, would probably contribute to a greater response. And that's an interesting observation, and perhaps also not surprising as well. So that's a very, very interesting observation brought forward.
Okay, we had a foot of wet soil in the fall that likely froze. We now have 3 feet of snow in the fields. What do you think is going to happen with subsoil moisture in the spring?
I hope that snow infiltrates. Because you had a foot of wet soil that froze, also hoping for a fairly slow melt. Hopefully it stays in the field, and if you've got 3 feet of snow, you've got maybe 3 inches of water equivalent out there to go down in. If it goes in, you'll get pretty good profile recharge from that total amount of snow that you've got, plus the wet soil. So I would say actually you're looking pretty good in terms of having some subsoil moisture replenishment with that amount of snow.
Great, and this will be the last question before we jump into the next presentation. With talks surfacing in the recent years from the government, is there any work that is being introduced in fertility to reduce our use of fertilizer and continue to produce high yields? Thoughts on the reduction of fertilizer use?
Well, I guess in terms of reduction of tons of fertilizer use, kilograms per hectare of applied fertilizer use, and thinking about nitrogen, I think that we are working towards that in the precision fertilizer application endeavors that we're moving towards and are being employed here on the prairies, where we are looking to increase the recovery and maximize the use efficiency, and in effect obtain the same yield with a less amount of fertilizer by using it more efficiently, redistributing it across the field to where it's needed most, where you're going to get the greatest uptake. So I think you know, the kind of work that's going on in precision application, variable rate is moving towards that as well, and maintaining the yield. I also think that a lot of the enhanced efficiency efforts and also strategies for improving even more the precision of placement are working towards getting more of that nutrient into the plant rather than loss. And that means that if you're getting more into the plant and less is lost, you can cut back. That means for the same yield, you can achieve that with a lower rate if you're losing less of it before the plant gets a chance to use it. So yeah, I think we're moving in that direction, and it really involves applying those 4R principles to improve that crop recovery of the fertilizer.
Great. Thank you, Jeff. I will now hand it back over to Chelsea, and she
Great.
can introduce our next presentation.
Thank you. Bye-bye, folks.
Thanks, Jeff. Next up, we have Brianne McInnes. Brianne has been working for the Northeast. Oh, 1 second, guys. Brianne has been working for the Northeast Agriculture Research Foundation since the spring of 2018. She began working for NARF as the research assistant, but has since been promoted to the operations manager. She completed her Bachelor of Science in Agriculture from the U of S in 2018 and became a certified crop advisor in the winter of 2020. Throughout her time at NARF, she has enjoyed getting to conduct and develop research and demonstration trials while working collaboratively with other AgriArm sites, commodity groups, private groups, and various industry stakeholders. Brianne couldn't be here today, but David McTaggart will be stepping in to answer any questions that you may have at the end of the recorded presentation.
All right, hello everyone, and welcome to the third day of the Northeast Ag Update. I am Brianne McInnes, and I am the newly appointed Operations Manager for the Northeast Agriculture Research Foundation. This is my third year in a row presenting at the Ag Update, and I believe my title has changed every year, but I guess that's a good thing. I unfortunately won't be around after I am done my presentation. However, if you have any questions, I have asked our new Associate Research Manager, David McTaggart, to try to answer any questions if there are any. However, if he is unable to answer your questions, my contact information will be provided at the end, and you can reach out to me if you have any follow-up questions. We are also always looking for more producer and industry involvement in research and demonstration ideas. So if you would like to discuss any potential ideas, you can also reach out to me for that. I also just wanted to give a shout out to Miles from Shark Egg for these awesome drone shots. They turned out awesome. This is our plot area from the past seasons. So yeah, with that, I'll get started. So this may be a bit redundant for anyone who has attended our annual Ag Update before, but again, on the odd chance that you're not familiar with us and what we do, this is just a little bit of an introduction. So the Northeast Ag Research Foundation is a non-for-profit organization that has been in operation since 1997. We are a part of the AgriArm organization, which consists of 8 different producer-directed research and demonstration sites, and we're all located throughout the different soil and climatic zones within the province. We each run our own independent programs, but we often collaborate on government and commodity funded projects to compile multi-site and multi-year data analysis. At NARF, our research and demonstration program usually consists of anywhere from 40 to 50 trials in a typical year. Most work we do in recent years has been mostly small plot. However, we do a little bit of field scale work here and there. Most of our work is comprised of your typical large scale annual grain crops. However, we try our best to stay a little bit diverse and do some more work with some minor acreage crops like camelina, hemp, dry beans, sunflowers. We also did some more cover cropping research in 2021 with some different crops that are new to us. And we actually ended up working with more than 20 different species of crops in total this past season. We have a smaller forage program as well at our site. We collaborate with the Sask forage seed growers for this. So to run our research program, we work very closely with Sask Ag, the various different commodity groups, a little bit with educational institutions like the University of Saskatchewan, University of Manitoba. And then we also work a little bit with some various private industry partners. We are located just south of Melfort at the Melfort Research Farm. We work very closely with Agriculture and Agri-Foods Canada to operate and conduct our program. So these are just some lovely pictures we took throughout our season this year. You can see we have some different cropping options, such as dry beans on the left, sunflowers, you can see some red clover, flax, winter peas, faba beans, hemp. So we have a variety of different crops at our site. Although we had a relatively different or difficult season with less than ideal environmental conditions, everything emerged pretty nicely this spring at our site, and we were able to successfully harvest all our annual grain crops, much like a typical year, although harvest was much earlier than anticipated. And then again, yields were obviously a little bit lower than what we would see in a normal year, but overall, everything looked pretty good at our site this year. So again, here's what the conditions were like at our site. We experienced a whopping 0.2 millimeters of rain in July, which I believe was actually the lowest amount of precipitation as compared to all other agri-arm sites, even as compared to down in the southwest by Swift Current. So we were definitely very dry. Our soil's ability to retain moisture due to its fine texture, clay nature, and then a very high organic matter percentage, as well as some adequate soil reserves in the spring, really helped to allow for a successful harvest for us, even though again, yields were reduced, but our plots look surprisingly pretty good throughout the season. So this year I decided for my presentation to focus on some of the pulse research and demonstration projects we have going on at our site. Unfortunately, this is only a small portion of our program. However, if I went over everything, it would just take hours and likely bore you to death. So I'm just going to summarize and highlight any important findings from our pulse trials this year. Any fertility and disease-related trials, unfortunately this year, there wasn't a very great response. However, you will see, depending on a variety of factors, there sometimes was a bit of a response, but again, if moisture had been greater, results would likely be different, or treatments and responses would likely be a little bit more pronounced. So for our pulse crops this year, we had dry beans, field peas, and faba beans. And here are just some pictures of the different trials that I'm going to talk about here. So I talked about the first year of this demonstration at last year's AgUpdate. And we were actually successful in receiving a second year of funding for the 2021 season. This demonstration was funded in both years through the ADOPT program, or the Agriculture Demonstration of Practices and Technologies. The objective of the project was to evaluate dry bean response to increasing nitrogen rates under dryland and solid seeded management conditions. As I mentioned last year, a demo was completed in 2019 at a few other agri-arm sites where they found that nitrogen application yielded better results than using commercially available inoculants in dry beans. So the rates that were used in 2021 of nitrogen were a control with what's just available in the soil, and then 55 kilograms, 75, 105, 135, and 155 kilograms per hectare of total nitrogen. So the soil amount was subtracted from the applied amount to get those total nitrogen rates. In both years, residual nitrogen levels were on the higher side at our site. However, we still saw a nice yield and 1,000 kernel weight responses in both years. There was only a difference of about 8 pounds per acre of soil residual nitrogen in the top 12 inches of soil between the 2 years at Melfort. From the pictures, you can see that there was quite a difference in dry bean growth between the 2 seasons at Melfort. In 2020, we had a very wet and a much colder June. which led to much less dry bean growth, but there were also more noticeable visual differences between the treatments, as you can see on the left there. Dry beans like it hot, and so in the spring of 2021, we had much better growth, which with a much thicker crop canopy, as you can see. However, the visual differences between treatments was much less notable. However, you can see a slight bit of yellowing in comparison with the control on the right up top there on the high nitrogen rate on the left. Plant densities in both years was not significantly affected by increasing nitrogen rate. However, plant densities were higher by an average about 6 plants per meter squared in 2021 as compared to 2020. There was no height response in 2021. However, plants were on average about 5 centimeters taller in 2021. In 2020, plant height was greatest at moderate to high nitrogen levels as compared to the control. So in 2020, we had an early frost on September 8th, I believe it was, which minimized the visual maturity differences. However, in 2021, maturity was prolonged at 135 to 155 kilograms per hectare of nitrogen by about 6 to 7 days. The only disease we had in 2021 was bacterial blight in our dry beans, which was more prevalent actually as the nitrogen rates increased, but it didn't appear to really have any detrimental effects on final seed yields. Overall, seed yields were higher this season, but the same trend occurred in both years, with a positive correlation between increasing nitrogen rate, seed yields, and 1,000 kernel weights. There was about a 200 pounds per acre difference in seed yields between years as well, with 2021 having much higher yields in comparison to 2020. So this data does provide a nice contrast between growing seasons and the nitrogen responses. So like I said, we had a cool and wet spring last year, and then a hot and dry one this year, and we still continue to see a benefit to applying high nitrogen rates in dry beans. We did do a bit of an economic analysis this year. In 2020, however, we didn't. So I just kind of quickly threw one together using 2021 commodity prices, which again makes it a bit more profitable with the current high commodity prices. So keep in mind that the expenses may vary depending on operation and location, which could change your overall net profitability. But overall, yield gains were enough at the highest rate of nitrogen to result in the greatest net profits as compared to all other treatments. Also, the prices used for dry beans was the current price out of Alberta, I believe, of $121 per kilogram. David did complete this analysis, so hopefully he'll be able to clarify at the end if anyone has any questions on the economic analysis for this project. All right, so on to our next pulse trial. This was also funded by the ADOPT program. For this demonstration, we compared older versus newer green and yellow pea varieties under more basic and then more intensive management conditions. So for our varieties, we had CDC Meadow as our older yellow pea variety, and then CDC Spectrum as our newer yellow pea variety. So for green peas, we had CDC Razor as our older variety and CDC Forest as our newer variety. And then management varied based on seeding rate targets of either 75 or 100 plants per meter squared, 20 or 40 pounds per acre of total phosphorus, along with 10 pounds per acre of sulfur in the intensive treatments. And then lastly, the intensive management also received additional seed treatment and a fungicide application around early flower. So the pictures along the bottom here show the different treatments closer to crop maturity. As you can see, CDC Meadow on the far left had the earliest maturity and was much earlier than the newer yellow pea variety CDC Spectrum, which is just to the right of CDC Meadow there. And then CDC Forest is on the far right. And you can see that it is the latest maturing, but there's not much of a visual difference as compared to the older green pea variety, CDC Razor, which is just to the left of the picture of CDC Forest there. You will also notice that the older varieties are demonstrating more lodging as compared to the newer varieties of the same market class. This would obviously make a large difference in the ease of harvestability of the newer varieties as compared to the older varieties. When we get to our data collection for this demonstration, for plant densities, yellow pea varieties were more responsive to increases in seeding rate as compared to green peas. There was an average of a 15 plants per meter squared increase as well from basic to enhanced. CDC Forest was the least impacted by seeding rate and had approximately 70 plants per meter squared regardless of rate. CDC Razor had a slight increase at the higher rate, but only by about 6 plants per meter squared. CDC Meadow went from 63 to 89 plants per meter squared, and Spectrum from 71 to 98 plants per meter squared. So these results suggest that the yellow pea varieties were less affected by interplant competition. And then again, for maturity and lodging, I mostly went over them in the results in the previous slide. But just for any further clarifications, the differences in maturity between the yellow pea varieties was only on average about a 3 days difference, whereas in contrast, the green pea varieties did not significantly differ in their days to maturity. Again, overall, things matured relatively fast this year due to the stressful environmental growing conditions. So even though it was a 3-day difference, I mean, the difference in when we harvested them would have been like August 9th to August 13th. So in these types of growing conditions, it wasn't that big of an agronomic issue. So for yield, all varieties except Razor had comparable yields, with Forest and Spectrum yielding the highest at about 52 bushels per acre. Meadow was the most responsive to management with a 8 bushel per acre yield gain from the basic management to the intensive management. Forest had a 4 bushel per acre yield gain from basic to intensive, which was likely mostly impacted by the higher fertility, considering there were no differences in plant densities of the treatments, and there likely was little benefit to fungicide or seed treatment this year, but it's hard to really say for sure. And then with Spectrum and Razor, they were both not affected, which for Spectrum portrays that there really was no yield benefit to a higher plant stand, or that the greater level of inputs was able to further compensate for those differences in the plant densities of those two managements. For protein, the only effect was a variety. So CDC Razor had significantly increased protein as compared to all other varieties. But overall, the difference was very small at about 0.6 to 1.1%. For this demo, we also did an economic analysis. However, I included several different tables to kind of compare different potential outcomes and different input considerations. So the table on the left, the bottom left there, assumes the same price for both varieties, which the current price for green peas this week is $16 per bushel for green and $17.5 per bushel for yellow peas, which is, these are the prices, sorry, I should clarify, for the week of January 17th. So costs varied based on seeding rate, fertility, fungicide, and the seed treatment applied. Keep in mind, we targeted a certain plant density when seeding. So for instance, our source of Razor actually had a lower germ and a higher 1,000 kernel weight, which actually led to a higher seeding rate or a seeding cost. So for the table on the left, CDC Spectrum is showing to be the most profitable under basic management. You will also notice that both new varieties and CDC Razor are most economical under basic management. However, the yield advantage with Meadow under intensive management was enough to make this treatment more profitable than basic. When we started this project, the most common reason that green pea growers don't adopt those newer varieties was due to downgrading from higher levels of bleaching with the new varieties. So what I essentially did on the table on the right was assume downgrading to feed for CDC Forest, which for the week of January 27th or January 17th, the offer price was $13.62 per bushel. So you can see that CDC Forest under basic management is still being profitable here, but again, the difference from the older variety is much less. So now to make things even more complicated, taking into account another potential change, the top right table actually assumes a lower seeding cost for the older varieties, as these are more than likely being grown from saved seed. So although there would be somewhat of a cost associated with them, I reduced that seeding cost pretty much in half because you're not going out and buying these new varieties more than likely, or these older varieties more than likely. So although you can see this diminishes the differences in return between the varieties of the same market class, both newer varieties are still showing greater economic returns as compared to the older varieties. And again, this is just, economic analysis based on the week of January 17th. And, this could vary if green peas all of a sudden have a better price associated with them than yellow peas, as they have sometimes in the past. So, okay, now on to our last demonstration. So this was funded by the Saskatchewan Pulse Growers. This demonstration looked to evaluate faba bean response to maturity and disease with different agronomic inputs. So the trial was conducted at all but one agroarm site. So there were a total of 7 sites. However, I only have Melfort's site data right now. The first factor of this demo was seeding date, which was to target an early date of late April, which we actually accomplished this past season due to early snow melt. And then a delayed seeding date, which targeted mid to late April, which I believe was May 18th for us. So the second component was 2 seeding rates of 45 and 65 viable seeds per meter squared. So again, we're accounting for the germination as well as the 1,000 kernel weights. And then the last component was either no fungicide application or an application of Priax or Diax around 7 days after the first flower. So the pictures on the right are of the 2 different seeding rates. You can see that the first date is still in flower, while the earlier date is already starting to begin turning with some yellowing of the stems, which actually unfortunately did result in some lodging of the earlier seed date after a heavy wind event near the end of July. So again, because our conditions this year, disease was very minimal in this trial. However, there were still a few points of significance in the data that was collected at Melfort. So the plant emergence between seeding dates was not significant. However, the early date did have significantly reduced plant emergence as compared to the later seeding date. The early date had an average of 39 plants per meter squared, whereas the late date had an average of 44 plants per meter squared. Although not impacted by date, there were significant treatment differences between seeding rates as well, where the lower seeding rate had an average of 36 plants per meter squared, and the higher seeding rate had an average of 46 plants per meter squared. So for days to flower, as well as days to maturity, we collected both of these. So both were significantly impacted by seeding date, where the early date had a longer days to flower and a longer days to maturity in comparison to the late date. Again, days to maturity were quite reduced this season for most crops due to stressful crop conditions. So the same existed for faba beans. We had pretty early maturity compared to what we would normally see. And then even though the early treatment did have a prolonged days to maturity in comparison to the late date, it was still ready to be harvested earlier than the late date, which is again important to note. For disease ratings, overall disease was again very low, but you can see that numerically the incidence of disease was slightly higher for the early date as compared to the late date. And this is likely just due to colder conditions during when the early date began flowering as compared to how hot it was when the late date began flowering. Additionally, without taking other factors into consideration, overall fungicide application did reduce disease incidence 14 to 20 days after a fungicide was applied, although the difference was numerically quite small. So finally, when comparing seed yields for this demo, there was no significance between any of the treatment factors. Overall yields were also very low at about 16 to 17 bushels per acre, which is very, very low for our site for faba bean yields. When comparing 1,000 kernel weights, there was significantly reduced seed weight at the early date as compared to the late date. This suggests that the early date likely produced more harvestable seed overall, but the seeds were just of a lighter weight in comparison to the late date, which resulted in comparable yields on a weight per acre basis. And so we did have a fourth trial, which was looking at managing peas in Aphanomyces contaminated soils. However, I chose not to include that trial just because we really didn't have any significant results at the Melfort site this year. There were multiple sites involved, so you can kind of stay tuned for those final results, which will be shared on our website later this year. But just because there really wasn't any important treatment differences to note this year, I just chose not to include it in this presentation. And with that, I will wrap this presentation up. So if any of you have questions or would like to reach out to me, my contact information is listed below. You can also find us on Twitter at @NARF_Melfort or YouTube at the Northeast Agriculture Research Foundation. We also post all research and demonstration results once they are ready to our website at neag.ca. So if you're interested in learning anything more about these projects, those reports will be posted throughout the next several weeks or months. And then just lastly, thank you to all our collaborators and sponsors this past year, as well as our staff and all collaborating sites for their hard work in helping complete these projects. So yeah, with that, I will just open it up to questions.
Once again, if you guys have some questions, you can pop them into the chat box, and I believe David will be here to answer them.
Yes, absolutely. So first question popping up from Kara. Will you continue the faba bean study on maturity, seeding date, and fungicide for another year or multiple years to gather more information based on different environmental conditions? That is a great question. I don't know what the current status is on our funding from Sask Pulse growers, but it was interesting. I was just sitting in on the winter meetings for the Sask Pulse growers yesterday, and they had some good data that Lyle Cowell, who works for Nutrien out of Tisdale, brought up surrounding that there has been work done in the past on the seeding date effect of faba beans across many years. And what we have found pretty regularly is that the early seeding date does benefit your yield in the end pretty consistently. So we'll see. Hopefully we do have some more funding come through from Sask Pulse, but as of right now, I'm not sure whether that's been confirmed yet.
All right, well, that looks like it wraps up our question period. Thank you so much, David, for stepping in for that. And shout out to Brianne for getting us an awesome presentation there. I guess to conclude things, I'd just like to thank you all for tuning in to the 2022 Ag Update. I would once again like to thank our gold sponsors this year, Adama, Syngenta, TigerCell, CCAN, the SIA, Sask Oats, New Farm, MMP and Melfort, Coke Agronomy Services, Flying Dutchman Aerial Spraying, Corteva, UPL, Exceed Grain Marketing, Crop Pro Consulting, Bunge, BASF, and Affinity Credit Union. Thank you guys so much for sponsoring this year's event. And also a huge shout out to all our wonderful speakers we had these past 3 days. They were very informative presentations, and we just really want to thank you for your time. And once again, a huge thank you to Shauna, the president of the Northeast branch, for getting this together, and the rest of the Ag Update committee and the Northeast exec for just putting together this great event. A lot of work goes into it. So thank you guys so much. With that, we look forward to seeing you all again in 2023. Thanks for tuning in.